So let's talk a little bit about hyperbolas and what they are. I'll read what the book has here. What do paths of comets, supersonic booms, ancient Grecian pillars, and natural draft cooling towers for power plants have in common? They can all be modeled by the same type of conic. For instance, when something moves faster than the speed of sound, a shock wave in the form of a cone is created. A portion of a conic is formed when the wave intersects the ground, resulting in a sonic boom. So what they're saying is that shock wave created by a plane, when it hits the ground, it's a hyperbola. It's hyperbolic in shape. So a shock wave intersecting the ground forms a portion of the conic and results in a sonic boom. So I'm just going to continue with this next part, locating the vertices and foci of a hyperbola. So going to the shape of hyperbola. In analytic geometry, hyperbola is a conic section formed by intersecting a right circular cone with a plane at an angle such that both halves of the cone are intersected. This intersection produces two separate unbounded curves. So remember our conic section, if you saw the video I had for ellipses, if we have this plane that is parallel to the axis of symmetry, where it hits the cone creates these curves. These curves are hyperbolic. So as with the ellipse, every hyperbola has two axes of symmetry. The transverse axis is a line segment that passes through the center of the hyperbola and has vertices as its endpoints. So going through the center there. And the foci lie on the line that contains the transverse axis. So if we had this line going through here, the foci is going to be up there, and one's going to be down here. The conjugate axis is perpendicular to the transverse axis. That'd be going this way. I don't know if you can see my arrow or not. Going like that. Oh, hang on. Let me get my pencil out. Okay, so we have transverse axis is going like here. And you'd have foci that lie on that. And then you have that conjugate axis, which is going to be perpendicular to that. It has covertices as its endpoints. The center of hyperbola is the midpoint of both transverse and conjugate axes where they intersect. Every hyperbola also has two asymptotes that pass through its center. As the hyperbola recedes from the center, its branches approach these asymptotes. So what I'm going to show here, try to show here. So you have like an asymptote that comes along like that, and one that comes along like, I gotta go there. So you get those asymptotes, and this curve eventually approaches that asymptote. Every hyperbola, okay, I said that part. The central rectangle of the hyperbola is centered at the origin with sides that pass through each vertex and co-vertex. It is a useful tool in graphing the hyperbola and its asymptotes. To sketch asymptotes of the hyperbola, simply sketch and extend the diagonals. So what we'd be looking for essentially is creating like these rectangles. And the diagonals of the rectangles would be these asymptotes. So that's a pretty messy drawing now. Okay. So here's a better graph of it. You get your curves. You have your vertex, vertex, co-vertex, co-vertex. So you get that rectangle. This looks more like a square, but squares are rectangles. But not all rectangles are squares. And those diagonals of that central rectangle would be the asymptotes that these curves approach. And so notice on the transverse axis, you have, if you extend it out, you get the foci. So deriving the equation of hyperbola centered at the origin, let negative c and positive c be foci. So we have, I think it's in the next diagram. Yeah. Negative C0 and positive C0 are the foci of the hyperbola centered at the origin. The hyperbola is the set of all points xy such that the difference of the distances from xy to the foci is constant. That means we get these two. So here's the point. What's the distance to one foci? What's the distance to the other? Then we take the absolute value of the difference. And then it's a collection of all those points that have the same distance. Standard form is the equation of the hyperbola centered at 0, 0. So the standard form is going to be either x squared over a squared minus y squared over b squared equals 1. So this is the case if it opens sideways. So the length of the transverse axis is 2a, so a being the square root of what's under the positive term. The coordinates of the vertices are plus or minus a comma 0. Length of the conjugate axis is 2b. The b is the square root of the term under the negative part, the thing being subtracted. Coordinates of the covertices are 0 plus or minus b. So the coordinates of the covertices are 0 plus or minus b. I don't know if I just said that or not. The distance between the foci 2c is 2c. So where c squared is a squared plus b squared. And the coordinates of the foci are plus or minus c comma 0. I want a space there, one there, one there, one there, and one there. Okay. And the equations of the asymptotes are y equals plus or minus b over a times x. Now I want to point out this b over a, it's always going to be whatever is the square root under the y term over the square root of what's under the x term. And the standard form of the equation of the hyperbola with center 0, 0 and transverse axis of the y-axis. So this one opens vertically, up and down. So it has the y part first and the x parts being subtracted. But the way this book is writing it, so we have the a squared under the y squared, b squared under the x squared in this case. So unlike ellipses, a is not necessarily bigger than b. Okay, so, but the y part's the positive term, the x part's the one being subtracted. So again, the length of the transverse axis is 2a. The coordinates of the vertices are now this time 0 plus or minus a. Length of the conjugate axis is 2b. The coordinates of the co-vertices are plus or minus b comma 0. So kind of switch what was above. And then the distance between the two foci is 2c, where c squared equals a squared plus b squared. And the coordinates of the foci are 0 plus or minus c. And the equation of the asymptotes are going to be y equals plus or minus a over b times x. Again, this a was the part that's under the y, b is what's under the x. Note that the vertices, co-vertices, and foci are related by the equation c squared equals, oh, maybe I don't want to do that. C squared equals a squared plus b squared. When we are given the equation of hyperbola, we can use this relationship to identify its vertices and foci. So here we have a shape of the one opening right and left, and here's opening up and down. Okay, how to locate vertices and foci of a hyperbola in standard form. Determine whether the transverse axis lies on the x or y axis. Note that a squared is always under the variable with a positive coefficient, so if you set the other variable equal to 0, you can easily find the intercepts in the case where the hyperbola is centered at the origin. The intercepts coincide with the vertices. If the equation has the form, with the x part first, then it's going to lie on the x-axis, and we went through that already. And then if it's going to be on the opening vertically, it's going to be the y part first. It's going to be on the y-axis. And solve for a using a equals square root of a squared, c equals the square root of a squared plus b squared. So let's do a problem finally. Okay. And it says, identify the vertices and foci of the hyperbola with the equation y squared over 49 minus x squared over 32 equals 1. So, given that this one is centered at the origin, based on the form we see, our a squared is 49. Our b squared is 32. So a must be 7. Now c squared equals a squared minus b squared. Plus b squared. So c squared is 49 plus 32, which is 81. So c is the square root of 81. So since this is centered at the origin, our vertices are going to be located at 0, 7 and 0, -7. And our foci, excuse me, are at 0, 9 and 0, -9. Roughly speaking, we have something at 7 and -7. So this puts us at the foci that's at 9, -9. That's the idea there. Okay. This was a little longer than I expected. I meant to break it up, but I kind of feel like it's on a roll. So we'll continue the next video on hyperbolas centered at the origin.